going. Excellent. All right. Okay. I do have several things to kind of go over. The homework thing, I sent you guys an email already, so I'm not going to go over that, unless someone wants me to go over that in class. I do want to show you guys something for those of you who feel, I'm really, really bored in the pseudocode class because I already know programming, and I don't really want to, be bored by all of this stuff. I want to learn something new. Okay, and also for those of you who want to get some hands-on actual programming experience but don't want to spend too much time on learning the syntax and stuff like that, there are two places where I think you will find kind of interesting. One is called Scratch. You go to scratch.mit.edu. For those of you who have used Scratch before from a prior semester, this is version 2.0. It is different. Okay, they extended Scratch so that it is now even better than before. Okay, it's graphical programming, and the best part is it's kind of like YouTube in a way, because whatever script you write and you think, oh, this is a really, really cool script that I wrote, it can find the greatest common GCF factor of two numbers, and I want to show it to the world. And you know what? You can publish your scripts, your programs to the world. Okay, if you check out one of the other projects, like you find a game that's, wow, that is really quite cool. I wonder how they did it. Okay, you can actually download the source code from another project and inspect the code and find out how somebody else did something. Okay, so you can actually learn a lot and teach other people at the same time, because you can share your projects with other people. So this is one website like that. You have to join Scratch first. I don't know whether you have to do it or not to actually have membership first. I already have an account here, so I think I can just sign in and show you guys what it looks like. Some of the stuff that we talked about in this class, like conditional statements and pre-checking loops, Scratch has it too, so you can actually practice some of the programming concepts here. The other website is also from MIT, but this one is even more interesting. It's called appinventor.mit.edu. It is particularly interesting for those of you who have Android devices, and you say, well, I wish they made an app like blah, 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 okay? Well, guess what? You don't have to wait for someone to write an app that will do blah, 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 because you can do it yourself. So with this one, it is tied into a Gmail account. You can choose one of your existing Gmail account. Doesn't have to be a particular one. Even the one that the district uses is fine. Okay, so let me just show you how to sign in. This is at apps.losstudios.edu. I think I might have mistyped. Yeah, it will send you to the district website, which is okay. Just enter your username and password again. Oh, I did not. No, I don't want to change my password. Okay, this time cancel. There we go. Okay, so now you have to go back to the App Inventor website again, appinventor.mit.edu. And I will choose this particular account to sign in. And this is it. This is how you write an Android app. Okay, this is the screen. It's, for the most part, what you see is what you get. You can drag the buttons from the palette. So on the left-hand side, this is a list of palettes. You have buttons, canvas, checkbox, clock, and so on and so forth. And you can even have different types of sensors, like the accelerometer, location sensor, orientation sensor, and stuff like that. You can drag all those into your application instead as well. To actually write the program, you have to open up the blocks editor, which is in the form of a Java web start thingy. So it will ask you for permission to run it and stuff like that. Let me just open it here. If you use Windows, it would use a Java web start. It looks different, but it's just gonna pop up a few screens, ask you for permission, like this, and you say run. And it's going to start it up. This is a pretty fast computer, so I'm not going to have issues starting it up. There you go. So this is where you write your programs. The built-in tab here for these particular blocks also has control. And if you look at the controls here, we have conditional statement like if, okay? So you can drag and drop it into something. We also have pre-checking loops like while. So these are the these are the statements that we have talked about already in this class. So for those of you who want to kind of play with an actual programming environment and still be able to practice what we learned in this class, this is not a bad way. Okay, it's all drag and drop. There's no syntax to learn. For those of you who who already know how to type in C, C++, Java, and other programs, this may seem a little tedious because just to do a little thing you have to drag and drop a lot. But at the same time, you can also get your app up and running pretty quickly too. If you do not have an Android device, you can use an emulator. So you just click New Emulator, and it will start up a virtual machine, which is an Android device, and you can use that to see how your program is going to run on an actual Android device. When you're all done, you can also create an APK file, which is what people use to distribute applications. And if you have your market, on the Android app market, you can actually start to distribute and sell your app. So this is a fast track, to app programming for those of you, who already have some idea of programming and just want to get started with this. So are there any questions about this? I'm just kind of, yep.
What's the phone plugged into to be charging?
It's just emulated, So this is actually emulating. It's emulating, an actual device.
Yeah.
So it would still it has the same looks as a regular
Is that ice
phone.
cream or is that?
That looks like it's 2.3.3.
Yeah, this is really old. You can, if you look at, let's see, is there a setting? Yeah, you can go through settings and find out exactly which version of Android is running. So just click About Phone. And yeah, it's a really old version, 2.2. But the approach will work on a regular cell phone too. If you plug in your actual Android device, to the PC, then you're able to find it under here. In addition to these two items on the list, it will also show you the devices that are attached to your PC through USB. So if you have multiple Android devices, you can actually select one of them to be your debugging device.
You actually might have to enable developer options on your phone.
Yeah, you
it's
do.
already on.
Yeah, like tap that build number, what, 5 times, 7 times
It's
until
like
it
7
says
times,
you're
yeah.
now a developer. Yep. Yeah, but this is a interesting thing for those of you who are really kind of bored by having to hand trace everything. Even though you still have to do it by as your homework assignment, this is something that you can do on your own when you feel that, oh, I want to try something else, and I still cannot sign in. Reset password. I didn't ask for reset password. Okay, let me see if I can sign into this one. There we go. Okay, so I'm in Scratch now, which is basically the same programming interface. There are minor differences between the two. Let's see, create. And this is the programming interface of Scratch. They have the same root, but they're not exactly the same. Okay, so these two are related projects, but they're not exactly the same. This one is also the same thing. It's also drag and drop. You can go to control here, and you can find similar blocks, but I would not say exactly the same. We have the conditional statement, if then else. We have repeat until, which is confusing because this is actually a pre-checking loop, but it's looking for an exit condition instead of a stay in loop condition. So it's kind of like a while loop, a while do that we talked about in this class, but the condition has to be true in order to exit the loop instead of being false to exit the loop. Okay, so there are minor differences, but the same thing here. The nice thing about this particular app or this particular programming interface is it is very multimedia rich, and it has the capability to write games because it has the concept of a sprite. Okay, and when two sprites collide, it would be detectable, so you can actually write games in that way. So I just want to give you guys, some not so boring stuff to play with, for those of you who think, okay, I'm kind of bored with the stuff that we talk about in class, and you have something else to do like that. All right. I won't give you any homework assignments, with Scratch or App Inventor, but as we go over, topics like control structures, subroutines, and stuff like that, you can use the other resource to help you, get a better understanding of the material. All right, so I'm going into today's class, and you can see that we don't have any homework assignments due today, and then on the 12th we have the second homework assignment due. Just make sure that you observe all the requirements, the criteria that I already outlined. Yep. Roll sheet, very good. And I got something to say about the roll sheet as well. There is a new clean sheet, on the roll sheet, because the other one is kind of all filled in already. Pretty much, got one column left. But I'm starting a new sheet, so just use the front one, the new sheet, as your roll sheet. If your name is not on it because you're not even on the wait list, you just have to add your name. There's not a whole lot of space, below the last person on the wait list, so you can probably just put it on the back if you want to. All right, so I'm gonna start the roll sheet from here, and then we'll go ahead and continue our discussion of loops. Okay, we are done with pre-checking loops. Now we are working on post-checking loops. As the name implies, a post-checking loop is a loop where the checking of when are we getting out of the loop is done after the action. So you always perform the action at least once. Okay. Let's think about why that is even a good idea. Because remember, I think when I mentioned pre-checking loops, I said the majority of loops are pre-checking. Okay, you check the condition before you perform the first action. And sometimes you may not even perform a single action because if the precondition is false to begin with, you don't even perform a single iteration. So when do we need the other type of loop, a post-checking loop? Well, a post-checking loop is useful for situations like this. So let's say you're writing an app, okay, and you're asking an end user for a zip code, okay? We all know zip codes are 5-digit and cannot contain any letters and stuff like that. But there are only certain zip codes that are actually valid, right? Some zip codes actually do not exist. So let's say you have some way to tell whether a zip code is valid or not. Okay. So how would you describe the logic of not letting an end user proceed any further until a zip code, a valid zip code, is entered? How would you describe that logic? Go ahead. No? Okay. Yeah, go ahead.
So you have all of the zip codes, it would check the zip code that they have and see if it matches any of the ones that don't exist, and if it doesn't.
Let's say that logic can be described as validate. So we can tell whether a zip code is valid or not. Okay. Yep. Go ahead.
If it contains any alpha characters instead of numeric characters.
That's too much detail already. I have one condition that tells me whether the zip code is valid or not. So, just imagine that I can tell whether, if you give me a zip code, I can tell you whether it's valid or not. That logic is done already. Yep, go ahead.
If it's 5 digits?
If it's 5-digit. Okay, we're still getting into the logic of telling whether something is valid or not. So assume I already have the logic to deal with that part. Okay, I can tell whether a zip code is valid or not. I just want to lock up the process, until the end user gives me a valid, zip code. Okay, so how would you describe that logic? Well, first of all, do you think it's going to be a loop, or do you think it's going to be a conditional statement? What is the difference? What's the difference between a pre-checking loop and a conditional statement?
Pre-checking does it before, and then post is during the process.
Okay, well, a conditional statement is a one-shot deal, okay? You evaluate the condition once, okay? You choose which way to go, And then after you go either way, you proceed to whatever is following. So it's called a one-shot. But a loop is not. A loop allows you to go back to repeat an action, to reevaluate the exit condition. Yep.
Well, if zip code is not valid, then re-enter.
Okay, very good. Okay, so that's a really good starting point. The starting point is to utilize the only loop that we have talked about, which is a pre-check loop. So we say while zip code is invalid, do enter zip code, which means new zip code, and while. So it's a very good starting point because as long as the zip code is invalid, I'll keep asking the end user to enter a zip code. There's only one little minor issue with this logic. The very first time you get into this loop, which zip code am I checking?
The one they have.
That's before the end user has a chance to enter anything.
Conditional.
Sorry?
Before it becomes conditional.
It becomes, well, the first time I check whether the zip code is valid or not, I'm not checking any particular zip code because that's before the end user entered the zip code.
I see.
Okay, now there's an easy way to make this logic work. Okay, it's very easy. It's called copy and paste. So I copy whatever is in the action here and then just paste it before. Now I fix the problem because I first ask the end user to enter a zip code without any condition, and then I check whether the zip code is invalid or not. As long as the zip code continues to be invalid, I'll keep asking until it is valid. So this will get a trick. This will do it. Okay. There's only one problem with this approach. It is not the logic. It is the approach. What do you think is the problem with the approach that I just took? Yep.
Duplicitous?
Stupidness.
Duplicitous.
Duplication. Okay, duplication is not a good thing. Every time I use copy and paste, which I just did, you have to ask the question, is that really necessary? Okay, copying and pasting in programming typically indicates something can be done in a more elegant way. Now, in terms of elegance in programming, we're not doing elegant programming for the sake of oh, it just looks better. Okay, because people really don't look at the source code and say, oh, this is just really beautiful source code. We look at elegance as a measurement of whether your program is easily maintained or not. Okay, that really is why we go after elegance. And copying and pasting is inelegant. Okay, because with this it doesn't seem to be a problem because we're just copying and pasting one line. But what if inside the loop here is a big chunk of code like 20 lines? Copying and pasting 20 lines is not recommended. Why do you think that's not recommended?
Because if you have a mistake, it's hard to find.
Exactly. So if you make a mistake in the original 20 lines, those mistakes will also be replicated. So when you debug your program, you might find the mistake inside the loop, but will you remember to fix the copy that is now outside of the loop? Okay? So the more you copy and paste, the more chances you might be replicating a certain problem. So by the time you realize there is a problem, you may not be able to find all the instances, all the copies, all the clones of the original. Okay, so that is exactly why copying and pasting is not a good approach. So we want to avoid having to copy and paste altogether whenever it's possible. So the solution to this problem is like this. So I'm going to use my Inkscape here to draw a picture, and then we can just draw this picture step by step to finish the logic of how to fix this problem. Okay. So I'm going to zoom it in. And by the way, Inkscape is also available for Windows. So for those of you who want to kind of play around with Inkscape or something like this, it is available for Windows. It's very useful for making scrapbooks, okay? Because you can actually import pictures, rotate, do all the cropping and all kinds of other stuff. All right, so what we'll do here is I'm going to describe the processes that are involved. Okay, so one thing we are involved, the one action that we have to do here is enter zip code. Okay, so that's an action, and we also have a condition here, and I will name that condition as follows. Just on a second, let me fix the fill here. Okay. Specify no fill so it's not kind of blue. The condition that we are checking here is zip code is valid. Okay, instead of checking invalid, I'm checking valid. It has to do with the nature of this kind of loop here. Okay, so we have a condition. And let me group these two so we can drag both of them around at the same time. All right, I have an action, which is enter zip code. I have a condition, which is zip code is valid. That can either be true or false. Okay. Should I check the condition first, or should I perform the action first? Perform the action first this time, because now there is a dependency between the two. Okay. In order to check whether the zip code is valid or not, I have to first ask the end user to enter a zip code. So that's why I have to enter the zip code first. Okay, well, let's reorder these things in the picture a little bit. I put the zip code here, enter zip code here, and I put the condition here. All right. So it seems like if I were to draw a trail map representing the logic here, this action, after it's complete, I will go down here, and then I ask the question, is the zip code valid or not? Okay, because we perform the action first, and then we perform the action first, and then we ask the question to see whether we have to see which way to go, right? What if the zip code is in fact valid? What should I do next? Say again? I should end this particular statement so I can continue with whatever is after. Okay, that makes perfect sense. So that means, this is going to be a branch. Every time I have a question, you kind of have to say, well, that's probably a branch because there's one way to proceed like this. And I'll just draw an arrow here and then label this path here true. In other words, when the zip code is valid, I'm going to choose this branch to continue with whatever is following this particular loop. Is that making any sense? Okay. So the other branch is pretty clear. I should not proceed. If I'm not proceeding with the other branch, where am I going? Loop back. Very good. Okay, so with the other branch here, I'm looping back. So I'm going to draw a loop back symbol here. So this one is going to maybe loop back. So I'm going to draw another arrow just to indicate that this is a one-way street and that's where we are going. And I'll label this with what? False. Exactly. When the condition is false, that the zip code is valid, I'm going to go back. The picture is almost done. I just need to add one more thing, which is the entry point of the entire loop here. So this is my entry point coming in like this. This is a loop back point. Oh, that looks ugly. Fix that. There we go. Slightly better. All right. So now we have our post-checking loop. A post-checking loop looks like this. We have an entry point, and then before asking any question whatsoever, we perform the body, the action of the loop. But after we perform the action of the loop, then we ask the question. Okay? The question here is whether the zip code is valid or not. It is also called a terminating condition, or it's also called a terminating condition. It's also called a, trying to remember the name of this, exit condition. Okay, it's also called an exit condition because when the zip code is valid, we're going to exit the loop. It's also called an exit condition. So this is the shape of a post-checking loop. And then what we'll do next is to put this one on the side, and then we'll take a look at the actual pseudocode representing that. Okay, so let's scroll this one out of the screen so it's not confusing us. And we can now say, this is, in pseudocode in this class, it is repeat, enter zip code, which is the action that I might have to do again and again, and then until zip code is valid. That's how we write a post-checking loop in this class. the polarity of the condition is actually reversed compared to a while do. In other words, in this case, when the condition zip code is valid, is true, we get out of the loop. In a while do loop, when the condition is false, we get out of the loop. Okay? In certain programming languages, such as C, it doesn't have repeat until. So when a programming language has no repeat until, it usually has the alternative to this. So in C, you would have said do enter zip code while zip code is invalid. They mean exactly the same thing. I just have to flip the polarity because certain languages only look for a condition being true to exit, and others look for a condition being false to exit the loop. But these two loops are identical in terms of the structure, because both of them will check the condition after the action, and therefore they're both post-checking loops. Are there any questions about the picture representing the logic and the pseudocode, which is a much more concise way to represent the same logic? No questions? Okay. If there are no questions, I'll give you a trace, because we always want to follow up a discussion of control structure with at least one example of a trace. So this time we'll start with, I'm debating whether I should start with something that's tricky or not. Let's do it that way. Let's start with something that's a little bit tricky. Yes, slightly challenging, but not too much. Okay, so we'll say, since I'm not starting with my persistence drive already recognized, I have to redo this part again. It's okay, it won't take too long. All right, so now we have variable x getting a value of 5, okay? And then we say repeat, x gets x plus 1 until x equals 5. And that's it. That's a tricky one. All right, that's the pseudocode I want to trace, and here I'm going to open a new window to trace that pseudocode. Be able to resize it first. There we go. All right, before I even talk about the trace, maybe you should spend a little bit of time. I'll give you guys like 30 seconds to kind of think about it while I do the formatting. So these are the usual stuff to begin trace. Okay. So are you guys, can you kind of think of what this code might do? Okay.
The infinite loop.
It's an infinite loop. Well, I would say it's close to an infinite loop in the practical sense, but logically it is an infinite loop. Okay, so in theory it is an infinite loop, but in practice it is not exactly infinite, but it's a bad one. Okay, so I'll explain that later too. Okay, so here we go. We have line 1, and line 1 is pretty easy. It's an assignment statement. We evaluate the right-hand side, change the left-hand side accordingly, so x is going to end up with a value of 5. Here comes the problem. Because when someone who did not understand the picture that we drew earlier and look at this code, that person might actually skip the action and go all the way to line 4 and say, oh, until x equals 5. That means we're done already. That's nothing to do. But unfortunately, that's not what the program is going to do. That's not the behavior of a post-checking loop. The behavior of a post-checking loop is we always perform the action at least once. So that means I have no choice but to go to line 3 right now and change the value of x from 5 to 6. Then we proceed to line 4 and evaluate the condition. X equals to 5 is false, because now it is 6, right? And then where do we go?
3.
Well, the condition, the exit condition is false. I cannot exit yet, right? If I cannot exit, I have to go back to perform the action again. So I'm going back to line 3, not line 2, because line 2 doesn't do anything other than marking the beginning of the of the loop. So I go back to line 3, it goes from 6 to 7. I go back to line 4, x equals 5 continues to be false, right? So now the question is, I can probably make a conclusion and say, okay, this x can never be 5 again because it is only increasing. Okay, it has gone past 5 already. There's no way it can get back to 5. Is that making any sense? Yeah. In a math class, that would make perfect sense. In a programming class, it makes sense, but that's not how it's going to work. Okay, this loop will actually exit. Isn't that weird? Okay, it has to do with how are numbers represented in a computer. Okay, how do you think numbers are represented in a computer?
Binary.
It's represented in binary, which means it's in base 2. Okay, whether something is in base 2 or base 10, it really doesn't matter in this case. It has to do with the number of digits that we allocate to each variable. Are we doing okay so far? In other words, when we refer to x as a number, okay, let's not even think in base 2, let's think in base 10, okay? So we have a variable x here, and it is capable of storing a particular number. But I cannot allocate an infinite number of digits to variable x. Why can't I do that?
It's resource limitations.
Resource limitation, because as much memory as you can put on a computer these days, the gamers in this class can tell me that you have 16 gig, of RAM on your computer, right?
Yeah.
Does anyone have 32? Not yet? Okay. Are there motherboards that can do it now? 32 gigs? Okay. But even 32 gig is a finite number, okay? So as long as it's a finite number, this number can only have so many digits associated with it, right? So let's say this is a base 10 number. Let's say we're representing everything in base 10. So even in base 10, if I give it 8 digits, then the largest value, let's say we're only representing non-negative values, okay? So we just take negative numbers out of the equation for now. It can only store a number up to 99999999 in base 10. And if you add 1 to this, it can no longer represent the next larger value. So here comes the tricky part. What if x already had this value, because I have been running this loop for a while, and in the next iteration, I'm going to add 1 to it. If you add 1 to this number, it becomes the first number that is too large to be represented by 8 base 10 digits, right? That makes sense. In Visual Basic, it would have given you a runtime exception. In other words, it would pop up something on the screen and say number out of range, value out of range, or something like that, and it would tell you which line number is causing that problem. In other words, the program would just basically quote-unquote crash, okay, but not in a really bad way. It would just tell you that I can no longer continue execution because the value you're trying to store cannot be represented. The program would just stop execution in that case. But you are moving on to cisp300, which means you're going to write the program in C and C++. In C and C++, the next number becomes that again. It wraps around to 0. Well, once you wrap around to 0, it will just take 5 more iterations to get back to 5, and then you will get out of the loop. Okay, so even though in theory this is an infinite loop, okay, to computer scientists it is an infinite loop. To mathematicians it's an infinite loop. To anyone who would formally analyze an algorithm it's an infinite loop. But when you run it in C and C++, it is not infinite. It will wrap around and get back to 5 eventually, which is very bad. Because your program will just appear to run very slow, it seems to be stuck, and then at some point it will just get unstuck and continue execution. But in between, it will have plenty of iterations where x, the value of x, is well exceeding 5, which means the rest of the loop may not be able to handle x being 10,000 or whatever. Okay, that's another reason why the C programming language is really quite dangerous, especially for novices, because it hides problems like these from you, which is Not good at all. Okay. Are there any questions about this particular example and why this is an infinite loop? Even though it seems like, it's not an infinite loop, it is.
Actually, just
Yep.
out of curiosity, is there a way to actually make that infinite?
To make it truly infinite?
Yeah.
Yeah, sure. There's a way.
False.
Okay, if you want to truly make this infinite, you can make this add 2, and then you're looking for 4. That will make it infinite. In fact, if you make it 4, you can pick any even number. It doesn't even matter. You can pick the next. Okay, make it 8. Oops, I forgot to press the enter key. You can make this 8. This is an infinite loop.
No, that makes sense.
Because the wraparound is not going to change whether it's even number or odd number. So this is an infinite loop. Nothing will save you in this case. Okay. Let me kind of go backtrack a little bit. Even though it's not really the core content of this class, I'm using this because we're all familiar with base 10, right? I mean, we use base 10 on a daily basis. But inside the computer, as you said, it's in base 2. Okay, we're using binary numbers. In other words, everything can either be a 0 or a 1. Okay. How would you count numbers when you can only use zeros and ones? It sounds kind of complicated, right? Base conversion. Okay. I want to tell you one thing, and hopefully you will remember how easy it is. Maybe not the exact procedure, but if you look at a problem in a certain way, it can make that problem a whole lot easier. So let me just teach you base conversion, and I'll give myself 2 minutes. Okay. Our money system at this point has all sorts of different values, right? Because we go from a penny to a nickel to a dime to a quarter, and a quarter usually skipping the unpopular denominations. We'll skip to a dollar to 5. I know there's a $2 one, but most people don't have it, don't use it. $10, $20, $50, $100. Okay. Does anyone? I'm not seeing any repetitions here. No, not in a cyclic way. Okay. If you look at the ratio between these things, the ratio itself is not repeating in a cyclic fashion. I can see that there's a 5 here, and there's a 5 here. There's a 2 here, there's a 2 here, but then it's a 2.5 here. It's only a 2 here. And from here to here is a 4, from here to here is a 2.5, and then from here to here is another 2. So if you look at the ratio between the next denomination, there's no repeating pattern. And yet, do you feel confident enough that you can work at a McDonald's when the cashier is broken and you have to make the exact change to somebody? Do you feel comfortable and confident that you can use the least number of bills and the least number of coins to do it? Yeah. Not give someone 10,000 pennies or something like that.
Yeah.
Okay. You feel confident, right?
Yeah.
You know base conversion already, because in base conversion, in base 2, we look at this and go, this is really messed up. So what we do is we start with $1 bills, then we have $2 bills, $4 bills, $8 bills, $16 bills. Can someone predict the next one? 32, 64, and so on. On the other side, we have half-dollar bills, 1.5, $quarter bills, and if you want, you can have an $8 bill if you want. I mean, a coin for eighth of a dollar. Okay. Do you see any regularity on this side?
Yes.
It's all off by 2, right? Now, if I give you these denominations, can you still make a change, that is exact and use the least number of bills and coins? I'll give you one example, okay? So let's go over one example so that we can say, oh yeah, we know base conversion now. Okay, so I'll use another color. It's not recorded because it's really off topic a little bit, but I want you guys to remember this. Okay, so let's think about, I don't know, let's think about $19 and $0.375, okay? Because I have to make this work with base 2 system, okay? So how do I make a change, okay, of $19.375, but only using these particular denominations?
Start with the 16.
Start with the 16. What is the logic of that? 16 is the largest integer that is less than or equal to the amount. Okay, very good. Okay, so you got the logic already. Okay, we start with any value, the largest value that is less than or equal to, because if this is $16, we'll just give the other guy a $16 bill and we're done. Okay, so we have 116, so we'll just say one of these, and how much is left? $3.375. Okay, excuse me, $3.375. What is the next value that you'll pick? 2. Very good. So we got one of these, and then we have $1.375 left. What is the next one? One of these. Very good. We have $0.375 left. What is the next one? Quarter. Okay, a quarter. But it's the same logic, right? Even though now we are moving to values that are less than 1, it's still using the same logic. Okay, we have one of these quarters here. Do you realize, have you realized that we are only dealing with only 1 or 0 of a particular value? Okay, what is the next one? Just 1 of a $8, right? 1/8 of a dollar. Now we have 0 left, which means we're done. Okay, so we got one of this, one of this, one of this, one of this, and one of this. I don't see a binary number. Sure you do. I still don't see a binary number. Sure you do. It is 0010011.011. That is your binary number. Yep.
Why do you include the leading zeros?
Well, the leading zeros are here because it's just like in base 10, you can have your leading zeros, or you can just not mention the leading zeros. It doesn't matter. But since I have the 0.64 dollar bills, I just mention that. Okay. Yep.
What happens when you have an amount over like $128?
Well, I'm making the assumption that you have this goes on forever. So the next one is 128, 256, 512, 1024, and so on. Yep. But that's the approach of base conversion. We just did a base conversion from base 10 to base 2. Yep.
If you go on the calculator on the any PC, put it on programming or scientific, then you click on them and it'll.
I'm not sure whether they can do fractional base conversion, because I know you can do whole numbers
I mean,
for sure.
yeah, you can get numbers and just kind of play around with it.
Yep. But knowing this approach, means you can do it to any type of base.
Yeah.
If I give you like base 3, it's the same approach. In base 3, we have 1, 3, 27, 81, 273, and so on. And then on the other side, we have 1/3, 1/9, 1/27, and so on. But the approach is the same. Yep.
So it always starts at like the $1.
I always start with a 1 because it's just easier to see it this way. Okay? But now you understand, the base of a number system really is not that important. Okay? The approach of doing conversion is actually pretty simple. There's no particular reason why we have base 10 other than the fact that we have 10 fingers.
Yeah, there's some mathematical study about how E is actually the ideal base.
E
for thinking.
Natural log.
Mm-hmm.
I would say base 2 is good because imagine the base. Imagine the multiplication table of base 2. Okay, in base 10, how much time do you think I think it's either 3rd or 2nd grade. I think is it 2nd grader? I think it's 3rd grader. Okay, so how much time a 3rd grader needed to memorize a multiplication table? Even with all the duplicate items, not having to be remembered, all the trivial items do not have to be remembered, you still have a pretty good size number for a 3rd grader to memorize all the things, right? Well, in base 2, there's nothing, really nothing to remember. The multiplication of the multiplication table in base 2 looks like this. Right? Because you can only have zeros and ones. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. I'm done. Mom, I'm done with the multiplication table. Really? You just spent 5 seconds. Yes, I really know the multiplication table now. I'm not kidding. Okay, how long does a 3rd grader need in order to understand 5 plus 9 in base 2 can be considered as 4 with a carry? There's quite a few combinations here, right? I mean, 3 plus 9 is 2 with a carry, 8 plus 8 is 6 with a carry, and so on. And there's another, the flip side of this would be for subtraction, right? 5 minus 9 is 6 with a borrow. Okay? Those are all pretty, it takes a lot of memory and time in order to memorize everything. And even so, you can make mistakes, pretty easily. I mean, they can step on the little landmine in the calculation, and then it throws off the entire calculation. With base 2, everything is like this. It's easy. Okay? So if we want to save the time, to have kids to actually work on thinking problems instead of memorization problems, base 2 is the way to go. Okay? Because with base 10, there's a lot of memorization that has to happen, but that's really taking time away from kids from actually doing things that are challenging. Okay? Things that actually involves brain cells and actually thinking, because they're spending all that time to memorize a table that today is no longer necessary. We got computers and calculators, and we can free our minds from having to memorize all that stuff. Okay, so I just took a little digression, but I'm hoping that some of you will find this useful down the line in computer science or computer engineering, because it's a way of looking at things. Okay, I'm just looking at things from a different perspective, and that's base conversion. If you can make a change correctly at a McDonald's, you can do base conversion, because making a change is actually far more complicated, because you have to memorize all of these numbers here. Whereas with the other one, there's nothing to remember, nothing to memorize. All right. So I'm feeling we'll probably go through some of this again in this class. Okay, we'll write a base conversion program at some point. For those of you who cannot wait, you can use Scratch to write one first. It's not that hard. I mean, it really is not that hard. All right. So we are pretty much done with loops now that we are done with post-checking loops. So we'll go ahead and continue our discussion with nested statements. And I haven't fixed this one yet, and I'm kind of surprised that no one mentioned it. that really meant nobody actually had clicked on it and go, how come this is not showing up? I knew about this because my other class complained about it and go, hey, it's not showing up. It has to do with, it's trying to display it in frame, but for some reason it's not working. So I'm just gonna click open here, and okay, it's completed on this too.
I went to it from the main site, and it looked like, from some profs.com, and pulled up.
It should open. There we go.
Yeah.
All right, so this is about nested statements. Before I talk about nested statements, let's talk about something else that is nested by its very nature and is structured for necessity. So I'm not talking about nesting just because, we're going to talk about nesting because we have to talk about nesting. Okay, so I want to talk about nesting in the context of why is it useful. Okay? How much is a 3 terabyte hard drive, if you want to buy one from Fry's today? $100, okay. So they're getting fairly inexpensive. Storage, mass store is getting inexpensive every day. Okay. So let's say you go buy a new 3 terabyte hard drive. You try to get it to, into the system to expand your storage. Okay. And it comes with only one restriction from whatever operating system you're using. You cannot have folders. on your new 3 terabyte hard drive. You get your D:// and that's it. All the files that you want to store in your 3 terabyte hard drive have to be stored at the root portion of the entire drive level.
Can I have tags?
Tags?
Metadata on it.
Even if you can have that, you cannot have the same file name twice, right?
No, that's fine. I'll be all right.
That is what it is without nested statements in programming. Okay? Because you cannot organize the logic anymore. It is not structured anymore. So nested statements means certain types of statements are like folders. You can actually have other statements or even other folders within a folder. Okay? Is that concept okay with you guys? Okay? In a file system, you can have a folder inside a folder, right? And eventually, most folders will end up with a file or two, okay, or some more. But you can definitely have a folder within a folder within a folder. Is that concept okay? Okay. So once we understand the concept, then we can take a look at nested statements and say, oh, okay, so what is it about nested statements that makes it kind of special? So what I want to do is not to read the notes. I mean, that's something you can do after the lecture or before the lecture. What I'll do is I'm going to give you a sample program that has this particular nature to it. Every program that we have written so far that has loops and conditional statements are by their very intrinsic properties nested. Okay, but we'll make this one kind of explicit. Okay, so this is an explicit nested statement. So we'll go ahead and write something based on the loop. Okay, we have x gets a value of 0. While x is less than 5, do the following. If x is less than 3, then x gets x plus 1. Else x gets x plus 2. And if, and while. And we'll just take a look at this one. I'll leave it like this for now, because I also want to emphasize the importance of indentation. Okay, so this one has no indentation whatsoever. Everything is aligned to the left. Okay. And then what we'll do is we'll try to trace this program. I'll change it later to have indentation, so don't worry, we'll fix it. All right, so we'll trace this particular program. We have conditions to evaluate, so we need one column for comments. We have line number, we have a single variable x, so those are the columns that we need. And because the first thing we do to x is to override it with a constant, it doesn't matter what value it had before this algorithm. So the precondition can assume that we don't know anything about x. On line 1, we initialize x to 0. And then on line 2, we evaluate x is less than 5. It is true at this point. And then where do we go? Then we go to line 3. Okay, so this part is still okay. We go to line 3. We evaluate the other condition, which is x is less than 3. That is also true. And then where do we go? We go to line 4. Very good. So drilling in is easy. Now that we are at line 4, what are we going to do? We're done with line 4.
Let me go back to 3.
Sorry?
You said x to 1.
Well, okay. After line 4, do we have anything else to do in the then branch? No. Nothing else, right? So if we don't have anything to do within the branch that we have taken, we have to get out of the conditional statement. The conditional statement is inside the while loop. Are there any other things I have to do within the while loop? Is there any statement after line 7, which is the end of the conditional statement? No. So after you perform an action in a pre-checking loop, what do? You go back to re-evaluate the condition. So knowing that now, which line should I go back to?
2.
We go back to line 2. All right. So
you didn't
that,
insert the value for x.
oh, okay, we have to update it to 1, then we go back to line 2. All right, very good. So that's why we want indentation. For the first thing I want to illustrate is what it looks like with indentation. With indentation, it looks kind of like folders, right? When you look at, when you look at the Explorer view, in your file system, it uses indentation to show you this folder contains these folders, and then this particular folder contains, those folders, and so on. So we are already familiar with the use of indentation to indicate the level of nesting. And we are going to use exactly the same thing in programming, because now it is really quite clear what is contained in what. Line 4 is contained within the conditional statement. The conditional statement is contained within the while loop. Okay. What about the picture? Okay, I know I said we probably won't be using pictures a lot in this class, but let's just take a look at this picture here. How would I draw a picture for this particular algorithm? How would you draw a picture for this particular algorithm? So let's take a look. I'm going to do this real quick, so it's not going to be a very pretty picture. It'll work. Okay. All right. So here we have our electronic whiteboard, and I'm going to draw a picture. All right. If I look at this program from the top level, how many statements do I have at the very, very top level? In other words, if this were in a file system, how many items do I have in the root portion of the folder? 2 items. 2 items. We have line 1 being an assignment statement at the top level, and then we have line 2 to line 8 being a single statement because it's a pre-checking loop. So we only have 2 things at the very, very top level. If I were to draw a picture representing this logic here, this is one way to do it. Okay? So I have the entry point to the entire algorithm. I have something simple to perform here, and that's why I give it a little small notch. And then the next thing is a loop. So I'm going to give the loop a little bit more space because I know it can be complicated. But from the overall perspective, this is the overall program. Only has 2 statements. Now, one statement is real simple. The assignment statement, real simple. But the second statement, which is a pre-checking loop, is kind of complicated by itself, and that's why I gave it a lot of room. So this is how I look at this program. Now I can zoom in and say, okay, let's deal with the first statement first because it's really simple, and as a simple statement, we'll just go ahead and write it out. It is x gets 0, so x gets 0 is here. Okay. Are we doing okay so far with this picture? Inside the second statement by itself is a loop. Do we know the shape of a loop? I don't need to know about the details at this point. I just need to know the shape of a pre-checking loop. So what we're going to do, if I had a template, I'll just go to my template and say, okay, give me the template of a pre-checking loop. Slap it there, resize it, then I can fill in the details. But since I don't have a template, I'm going to have to draw it here by hand. But it won't take me too long because I already know how to draw one. Loop itself has its own action to perform. So I'm going to use this big block here for its action. And then after the action is performed, we have to go back to the beginning of the loop. There we go. And then we can close this. Looks kind of ugly, but close enough. All right. So that's the general shape of a pre-checking loop. I know it's really ugly, but let's just focus on the concept. Okay, this is a pre-checking loop. With any type of pre-checking loop, we have a condition to evaluate. What is the condition that we are looking for, that we are checking? Let's go back here. Which condition should I write, where it was blinking before? X is less than 5, because that's the condition of the loop. I'm not quite at the conditional statement yet. I'm still dealing with the loop. So you can see what I'm doing here is I'm doing this layer by layer. Okay, I'm going from the outer layer first, and X is less than 5 is the condition of the outer layer. So that's the outer layer question to ask. If the condition is true, we go here. If it is false, we go the other way. Okay. What is inside the loop? Inside the loop, we have a, how do you call this kind of statement here? Is a conditional statement, right? How do you draw, what is the shape of a conditional statement? Straight down and then what?
The branch.
Branch to do sides. Each side might have something different to do, and then what do you do after that?
Emerge.
Emerge, and then exit, right? So we'll draw that in the picture. So that means inside this loop here is a conditional statement. So now we will, if I could, I would use a template, but since I don't, I'm gonna draw this real fast. So, oh, that's really ugly. But that's okay. This is not an art class. Okay, so now we have our conditional statement. What is the condition of the conditional statement? What should I write here? X is less than 3. Okay, so X is less than 3 is the question I have to ask. Now, if I am going to be a little bit more complete, I'm going to have to label the branches. This is true, this is false, this is true, this is false. Okay. So what do I put here? The true branch of the conditional statement. What am I going to do? Going back to the source code here. X gets X plus 1. Okay, very good. So here we have X gets X plus 1. And then here we have X gets X plus 2. And now we have our entire pseudocode in a pictorial form. Okay. And you can see how it is quote unquote nested. Okay, the whole thing about nesting is if you look at the conditional statement, the conditional statement is this portion, but it is completely contained within the loop. Okay, so it's nested inside the loop here. Are we doing okay so far with this picture? Now, if I were to look at this, let's go back to Scratch because we want to see how we can actually do this part in Scratch. And Scratch is optional. Okay, this is definitely something that you do not have to do. But if you were to use Scratch to write a program like this, this is how it's done. Okay? You go to Control here, and first of all, we need a variable. So if you need a variable, you go to Data, you create a new variable. We just call it X here for this sprite, and now we have a variable X. The program can start based on a few things. You can start a program using the green flag. So when I click the green flag here, it can start the execution of this particular program. The first thing I want to do is to change the value of X to 0. In Scratch, it is called set X to 0. And then we have a loop. A loop is a control structure. I go to control here. And this is where things get a little bit confusing because it doesn't have a while do, it has a repeat until instead. So if it has a repeat until, and we are looking for X being less than 5 to stay in the loop, what is the condition to get out of the loop? When X is greater than or equal to 5, or it is not the case that X is less than 5. So that means in Scratch, we have to invert the logic. To invert the logic, you go to operators, you select not, which is the negation operator. We talked about this already. And then we have the less than comparison. We stick it here. We go back to data, and then we say X here, and then the 5 is constant here. Inside the loop, we have a conditional statement. A conditional statement is a control structure. So we go back to the control tab, and then drag and drop the if then else over here. And then once again we have a comparison. And this time we're comparing x to 3. Yep.
Why do you use a not instead of just x is less than 5?
Because this is a repeat until, so it is looking for an exit condition. If the condition is true, it gets out. Instead of the condition is false, it gets out. So that's why I have to invert the logic. Okay, so getting back to our pseudocode here, the true branch is x gets x plus 1. Now there's a quick and easy way to do it here because you can change x by 1, which is incrementing it by 1. So it's actually easier in Scratch in some way. And then the other one is incrementing by 2, like that. And that's my program. I mean, I just dragged and dropped my way, and be done with our program here. Are we still doing okay so far? Now, what Scratch does not do is it doesn't give you a trace. So for those of you who are thinking, hey, maybe I can use Scratch to do my homework, let the cat do my homework, right? Well, I'm sorry, it's not going to work out because Scratch can run, but it won't show you the steps in between. Okay. In other words, I can hit the green flag right now to let the program run, but it just tells you that when it's all done, x has a value of 5, but it doesn't quite tell you how it gets there. Okay. So but it is helpful in a way because it shows you very clearly that the loop is the container and is containing the conditional statement. The conditional statement in return contains the assignment statements that would actually change the value of variable x. Are we doing okay so far with this? Do you guys want to continue to use Scratch whenever it is appropriate, or do you think it's just adding to confusion? Because if you think it's adding to confusion, I can just not use Scratch until such time it is appropriate.
I think it adds to confusion. I think it adds to confusion.
Adds to confusion? Okay. All right. So we'll just make it optional, But how about this picture? Is it adding to confusion, or is it helping you understand how a statement can be nested within another statement? It helps? Okay. Now, you don't want to have to rely on the picture every time you see a nested statement or have statements nested. This is really just here to illustrate how a statement is completely inside another statement. Okay? But when we are tracing, we're not going to look at a picture like this. You might need to draw a picture once in a while, but hopefully, by I would say in about 2 weeks of time or so, you won't even need a picture anymore. You can look at the pseudocode and be able to tell which line is going to execute next. Okay. Well, this nested program is pretty easy. This algorithm with nested code is actually pretty easy. So let's go back to the notes here with a slightly more challenging example. Okay. And it's just slightly, not a whole lot more. That. It has a loop inside another loop. But it also has statements before the inner loop and one statement after the inner loop. I'm not going to finish the entire trace because 1, we don't have time to do it, and 2, it's kind of boring once you get a hang of it. So we'll just go through a part of this, okay? So we'll go over just a little bit of this. So this is not going to be a complete trace, it's going to be a partial trace. So do this and that. Okay, there we go. So I'm not even going to bother to retype the algorithm. The whole thing is being screen recorded anyway, so you can always go back to this moment, which is 11:42. If you want to write down the timestamp, this is a good, good time to write it down. So this way you can skip to this portion like right away and don't have to watch the entire thing. All right, so we'll go ahead and get started with this trace here. We have comments, we have line number, we have 3 variables in this case. We have sum, x, and y. And we'll go ahead and make them a little bit smaller. All right. The precondition is I don't need to know anything, even y. Okay, so all of these can be question marks to begin with. And here we start with line 1, x gets initialized to 0. Line 2, the sum s gets initialized to 0. And on line 3, we evaluate the condition x is less than 3 is true. Now, when the condition of a loop, of a pre-checking loop is true, we get inside the action. We get inside the loop here. So inside the loop, we have line 4 starting everything. So that's why we get to line 4. Line 4 is going to initialize y to 0. After line 4, we have line 5 actually just following it. That's why we have to go to line 5, which is the beginning of another pre-checking loop. Y is less than 2 is true because y has a value of 0 at this point. And that's why we have to go inside this loop here onto line 6. On line 6, y gets y plus 1, so y gets incremented to 1. And then on line 7, we add up all 3 variables to become the new value of s. And since this is a spreadsheet, I can do a little bit trick like this. I can just say it's this one plus this one plus this one. Press the enter key. I know, it's not exactly a good demonstration of calculation, but as you see later, it is actually going to come in handy being able to do this. Okay, and after line 7, where did we go? This is a good question because we are now at the end of a while loop, but there are 2 while loops. So which one are we ending, and which line are we going back to? That's the question.
We're ending the innermost.
Go ahead.
We're ending the embedded statement.
We are ending the inner loop, so that's why we are going to line 8. We're going to line, we don't trace line 8. We are done with the inner loop here. Okay, they're like parentheses, okay? So if you look at this as an expression, line 3 is like an open parenthesis, line 5 is an open parenthesis, line 7 is line 8 is a closed parenthesis, and line 10 is another closed parenthesis. So what is line 8 closing? Line 8 is closing line 5, so that's why we have to go back to line 5, okay? Line 5, because we cannot just go to line 6 because we don't quite know whether we should go to line 6 or line 9. We have to make that decision. So we have to go back to line 5 at this point because we have to reevaluate the condition for the inner loop to see whether we should continue with another iteration or whether we can get out of the loop. Is that okay? This is an important step. Now, since the condition is true, we have to go for another repetition of the inner loop. So this time we go to line 6 again. Y gets incremented to 2. And then we go to line 7. And I'm going to use the same trick here. Equal this cell plus this cell plus this cell. It is now 3. And we go back to line 5 again. But this time on line 5, y is less than 2 is false. Then where do we go? Okay, now where do we go is a good question because line 5, the condition, every time you evaluate the condition means there are 2 ways to go, right? Since we are not going for another iteration, we're exiting the loop. But when you exit the loop, the inner loop, which is from line 5 to line 8, where are you going to continue execution? Is there anything after that inner loop that I need to do? No. Not quite. Yep, go ahead. Oh, not yet. There's one thing I need to do after line 8. Line 9. Line 9 is an assignment statement that is following the inner loop immediately. So after we get out of the inner loop, we have to continue execution with whatever is after it. And we do have something after it, which is line 9. So this is why we are going to line 9 from line 5. And we have to add 1 to x. X goes from 0 to 1. And then after line 9, which is the last statement of the outer loop, where are we going? This time we go back to line 3 because it is ending the outer loop. So we have to go back to the beginning of the outer loop to see whether we have to go through another iteration of the outer loop. Okay? That is true. The condition is true because 1 is less than 3 is true. So now where do we go? We go back to line
4.
Yep, we go to line 4 and we just basically do almost the whole thing all over again. Okay? So this is not as trivial as the other one that we just talked about, because this one has another loop inside, and that's why it is confusing. The other one is simple because and if obviously is going to end the if, and while obviously is going to end the while. In this case, we have 2 whiles and 2 end whiles. So the question is, which one is ending which other one? Now, before we end today's lecture, we still have about 2 more minutes. Yep, go ahead.
So you would do line 4 and reset y to 0, and then go back to 5 through 8 again.
Yes.
Until your y value is at 2.
Yep. Okay, so for those of you who are more pictorial and want to have a picture, this is the picture of that particular loop. Okay? And it really shows you how something is contained within some other thing. And that's what you need to look at this whole thing. The most important part is after the inner loop is done, you have one more statement here before you can go back to the beginning of the outer loop. That really is the one part that most people miss is, oh, we got one little thing at the end. And this is a partial trace. I already did a partial trace for this particular algorithm. So you might want to go over that, just so that you have an idea of what is going on. And this one also has more comments, inside, so you might want to refer to that part too. Okay, we are running out of time today. I will see you guys on Thursday, and the homework assignment is due on Thursday, so don't forget that either.
What other class are you taking?